you all for coming to our lunchtime talk in science and math. We have a full slate of presentations for the semester, and this is, I guess, sort of the third, kind of the second. But it's my pleasure to introduce Professor George Sellman and the ASU Robotics Society.
Thank you, guys. Before I even start talking, I want to mention, so I don't forget, if you are interested in becoming a member, which really means just showing up, then you can, this afternoon at 5 o'clock, over in the outreach room, or in the community outreach building, we'll be meeting today at 5 o'clock, and every Thursday thereafter, give or take, not Thanksgiving, and maybe there'll be some canceled ones, you never know. But give or take, every Thursday. If you want to get on the mailing list, sign up here. If you just want to show up, you can just do that. And I've got things here if you want to figure out does everyone know where the community outreach room is?
Oh, the community partnership.
Oh, yes, sorry, it's Community Partnerships Building, yes. I'm sorry, I think of it the outreach room and I get it confused. So the Partnerships Building, the theater is just, well, south of us here is Richardson. South of Richardson is the Community Partnership Building. And it's the room on the north side of that. And we'll have the doors open and you can come and learn some stuff. So let's get rolling. So ASU Robotics Society, I have to say something. Bradley Sosisco really was the main creator of this PowerPoint, but he also made the template, right? Is Mike's here? Yeah, he wants credit for that, Mike.
I say we use it.
Yeah, it's nice. All the right colors and all that stuff. So, quick overview. Who are we? We'll do that. We'll talk about where we get money, because we have money to play with, to buy toys with. A little bit of the history of the whole project. Our laboratory, yeah. Let's see, I got to do this right. Competitors, that'll be clear when we get there, and goals. And then the box spot. Team members. We'll also talk, I'm also going to do hopefully a quick demonstration of programming a real basic robot. Here, let me hold it up for you. And that's what we're kind of about, and I'll talk about that a little bit. The basic robot may be built in half an hour, thrown together in half an hour just for fun. So you can see sort of the process that we go through, and see that it's not that big a deal. So elite team of robot building madmen and women. Definitely women in the group. We should have just said mad people, but mad persons doesn't have the same ring, does it? We're trying to build fully autonomous robots, constructed to scale the planet Mars. Yes, possibly other options are available. The focus here is on Mars a little bit. Here's some pictures of is the light? Let me switch the lights here a little bit. Are we on dim mode? Is this the? Yeah, that's a little darker. Okay. So this is pictures of the group right before the the robot challenge. And who funds us? Come on, there it goes. It's the Colorado Space Grant Consortium, and that's based at CU, Boulder. But it really is a consortium. They work hard not to make it Boulder-centric or CU-centric. And it's funded by NASA. They get a large grant, and they divvy it up to different consortium members. And the biggest thing that we've been working on over the years is the robotics challenge at the sand dunes, which is nice because it's local to us and we get a lot of opportunity that way. We also have, we've also been playing with robots. That's where this robot came from, for instance. And the walker, where did I put the walker? Oh, there it is. That was came out of the STEM, it's actually NSF STEM? No, it's Title V STEM. Sorry, I need to correct that. And we have a supercomputer grant which got us the Now robot, which is the white android. And I'm not sure we're going to get to him today or not. So how's the history of this? Why are we doing the sand dunes? Why are we pretending to be on Mars? Well, the inspiration is the Mars rovers, right? Actually the ones that went forever. They kept going and going. But Martin Marietta was contracted to build the Viking Landers for Mars. They chose as the story I hear, they chose the Great Sand Dunes as a test bed, which basically meant, hey, I know where there's sand dunes. Put it in the truck and let's drive down there. Right. At the time, nowadays, if you wanted to put motorized vehicles on the sand dunes, you have to, you have to have an extremely special permission, or else you can't. You have to stay east of the watercourse. But you'll see here, they were definitely not on the east side of the watercourse. They were right on the dunes. They put up their, not the actual Viking Lander, because that would be kind of messy, but they tested some of the equipment for it. Had 2 facsimile cameras. A facsimile camera, you guys, the day and age of cell phones, everybody's got a cell phone and you take a picture. So you say, why can't we just send that up to Mars, right? Take a picture, it'd be great. Well, at the time, this kind of technology wasn't available. So what they had is a facsimile camera, which had a single light sensor, a single photoreceptor, right? It's like if you had your eye and you only had one photoreceptor in the back of your retina, right? Okay, they place a mirror above it, and they take the mirror and swing it back and forth, and then scan it this way. So it does like a fax machine. It scans each line of the image and comes through. So it's black and white, but you can get, and okay, and this is the fun part. Let's get rid of the smart link here. I'll get it out of the way. That is the Martin Marietta Viking Lander team, right? But it really only consists of about 4 or 5 guys. Because what they did is, this is taken with the facsimile camera they were testing. And what they did is they lined up here. If you look closely, if we want to come back up, you'll see like this person right here seems to repeat. What they did is they lined up here. The camera moved along. When it got past the guy on the right, he moved around and got on the other side. And then the next guy came around and got on the other side. So it looks like a huge development team. So they're kind of fun. Uh-oh, it's finally dying on me. Right? Oh, there we go. I mentioned that this is black and white, but this is an actual picture taken with this camera. How did they do that? Anybody have any idea? Guesses? How can you take color with black and white camera? Yeah, that's true. They could have faked it. That's right. That's like the moon landings. Right. Yeah, but that's not what they did. That's actually a real color photo. What'd they do? No guesses? They took 3 pictures. Yeah, I see people saying, oh yeah, I was going to say that. Yeah. They took 3 pictures. They had filters. So they took one picture with a red filter, one picture with a green filter, one picture with a blue filter, and then they combined those. So let's see, is this going to work this time? Yeah, okay, good. This is the first image from the Viking Lander. It's like, you're going, what? Again, it's like, why'd they take, that seems like very unauspicious, right? Why take a picture of the ground? Well, the reason they actually chose this picture, the logic is very simple. If you were just plummeted to a planet, boom, right? And somebody took your blindfold off, the first thing you might want to do is look and make sure you have steady footing, right? So you might look at your feet and go, okay, where am I? Right? And that's what they were doing. Notice the foot is right here. So they're checking the foot to be sure that they're like not on the edge of a cliff. Like, let's not push that arm out this way because we'll fall over, that kind of thing. Second picture is a little more interesting, right? And it's just a panoramic view of where they were. Okay, so that's the Mars lander. So back to the sand dunes. Great place, obviously a great place. Martin Marietta thought was good enough for them for the Viking Lander. Well, it's good enough for us. So we have the Colorado Robot Challenge, which I forgot, we should have put Randy in the credits. Randy Emmons, former physics professor here, retired emeritus professor, I should say. Right, that's the right term. Really started this with the Space Grant Consortium. And got it off on its going. Excellent location for simulating Mars. Looks kind of like it. Water's a problem. Not much water on Mars, but the course isn't on the water. Here's a picture of last year's challenge. And these, you can see, oh, there's another picture here too. That's the Viking Lander to compare with. But this year, they actually built the courses and they tried to mimic terrain on, they tried to say this is like this portion of the terrain on Mars, this is like this portion of the terrain on Mars. I'm not sure how authentic it was, but, and I'll warn you too that oftentimes the course is always set up so that virtually it's always too hard for anyone to get through everything. So it's really, your measure of success is how much you actually succeeded on doing. And it is a challenge, not a competition. There's no award, there's no first place, second place. It's really just the group getting together going, gee, that's a good idea. Oh, that's a good idea. Oh, that's not a good idea. That kind of thing. These are some of the schools that participated last year. Fort Lewis, a lot of things. Let's see, we didn't list, oh, there it is. Yeah, Southern Utah University. We did have an out-of-state person come and group come last year, which was fun. The goals, the idea is to build autonomous robots to compete at the challenge. I'm talking too fast. But autonomous is the key word. So while it's very possible with the technology we're playing with these things, to build robots that we could control. In fact, I was working on that for the summer. You can control with a remote control or something and move them around. The object is to get the robot so it will find its way through a maze or avoid the obstacles and get there. And so that's one of the goals we have. Autonomy. One day making it to another planet. I would say that's true of some of our members already, but that's okay. Main goal, learning, yeah. And the main goal is learning, yeah. From both, and that's the other thing. It's a no-fault environment. If you want to come and be in the Robot Society, man, I'm going way too fast. But we'll have time to do the other demo I wanted to do. Go be a member of the Robot Society. If you have an idea, no one's going to say, oh, no, that's not a good idea. I mean, if you're, for proof, just come this afternoon and you'll see some of the things we've been working on. You go, whoa, okay. I can do better than that. So they're definitely, we're trying to be way out there, out of the box thinking. Teamwork, yeah, sharing ideas is the key thing here. Again, the reason we can fund this under the NASA grant and so forth is, you never know, maybe one of these robots will make it to the big time, but probably not, right? But the point is that this is all encouraging people to look at this technology and learn how to do this stuff and learn how to do the planning and learn how to work on a team on a technological project or any project for that matter. And finding common practical grant. Other opportunities, key thing that's happening with the space grant and has been happening. At Adams State, I said Adams State, not university. Didn't put the college in. At Adams State, we've been focusing mostly on the robot challenge. And just because it's accessible, it's easy for us to do. But I want to mention this, there are many other possibilities. First of all, if you're interested in learning how to use the Arduino, which is what our primary platform is right now, to do other things. You want to make, you want to put it on your skateboard, have an intelligent skateboard or a camera, or it tracks where you are in space, or who knows, or you want to put, Bradley was telling me about somebody who built a thing that they mounted on their door, and it's like a thin little dorm room door, and they hit it, and it makes a clinking sound like it's a steel door. So it goes clong, clong. If you want to try any of those things, all of these are possibilities. The consortium also has other projects that they do. They have what's called a balloon sat or demo sat, which is a high altitude balloon, and you build a payload. to go up in a high altitude balloon and take samples of whatever you think is interesting to take samples of, or pictures. There's some really interesting pictures of those, from those things. This year, there were reports back. Some people did Geiger counter, measure radiation at different altitudes. Some people were doing biology, watching, taking samples to see, looking at microbe distributions. Temperature, obviously, wind direction, pictures again. So if you have something you think might be interesting on a high altitude thing, you want to look for cosmic rays, you want to look for X-rays from thunderclouds, I don't know, that kind of thing. That's an opportunity. And then your payload goes up on the balloon pops eventually, you track it down and retrieve your data. They also have another one called a RockSat, right? It's not rock, rock is short for rocket, not rock. It's a RockSat, it's a catapult, no. And they fire a rock with your stuff on it. No, it's a rocket. So they send a rocket and the balloon of course does not get into actual outer space, right? Stays 25, 30 miles altitude, which is still pretty high. But at 50 miles is nominally outer space, right? The rocket will hit that boundary and go just past 50 miles. And then your payload, there's a couple different possible payloads. You can build one that's in a canister, safe and sound, has a little window to look out of, has other ways of measuring things. Or you can do a platform open payload. You can even do a payload that will eject itself from the rocket once it's up there. So you can do that. So there are people who've done that. They keep talking. So if you're interested in sending something into space, besides, like a sibling or something, but you can do that. They've been talking very regularly about trying to do an orbiting platform. It wouldn't be a permanent orbiting platform. It would be take an orbit or two of the Earth, maybe even a fraction of an orbit of the Earth, I'm not sure. But it hasn't materialized yet, but they're still talking about that. To get to the RockSat and the other ones, you would have to do probably a demo sat first, work your way up, play with this a little bit. So, and again, you can do, this is the sand dunes challenge last year. These are the competitors' robots. You can see they're pretty varied. This one was a fun one. That was Pueblo Community Colleges. I don't remember where those guys were from. This is Trinidad State. You see mostly wheels. We've been trying to, this year, try to steer, steer away from wheels? Oh, bad, okay, no. Oh, no. Anyway, so you can see those. And our entry last year is here, sort of with its guts opened up, if you're curious to come take a look. It's not operational right now. We're trying to rework it for this year, and then, so we have that robot to compete this year, and then another one that we'll be working on. The build, this is the build process of the Boxby. And you can see, last year we started out with the group, we built a kit. Those are hex walkers. I should have brought one of those, I forgot about that. That's another kit, that's a 4-wheel kit, just to get people used to things. And then this is working, right here, we're working on the kit, but back here they're working on the actual, that guy. And there's a shot of the box spot. There he is again. We're trying to get him programming. You can see he's got different wheels. We've tried different wheels. There he is out on the lawn. And there we are working. This is, these pictures are, those pictures are about a week or so, two before. This, I think, starts where it is the day before the challenge. Yeah, the wheels are different. Well, I'll tell you what happened was we went out with these wheels and another set of different wheels besides these wheels, these daisy wheels. And we went out to the dunes a couple weeks before, and we discovered they didn't work that well. But we modified them right at the dunes to those, and that actually worked very well. That's just sitting there being programmed. Oh, lost it. More of the same. Working. Getting the sensors working, which we didn't have the 2 weeks before either. We were a little closer time-wise. There we are, last minute. Here we go. That's at daytime on Friday. Late Friday. Right. Friday night, actually Saturday morning, I should say. We had a busy, we got it, and there we are, and that we got it working. Yay, okay. So, it was good. This year, okay, that's what I want to bring up. This, you can do this. People say to me, oh no, that's too complicated for me, right? It's really not that complicated. And excellent, I have time to show you that. You can, like I said before, you can take a look where we got started. This is the Arduino site. If you want to go, here, let's pull it up. The Arduino, an Arduino is simply, there's a good picture of it. That's an Arduino Uno, which is probably the most common thing to use to get started with these things. Very easy to, only nowadays, what, 25, 28 bucks or something, including shipping, right? Or you can get kits that come with sensors and things that, you know, range around the $50, $60 range. So it's not super cheap, but it's not like super expensive either. But the point is, it's very, very easy to get going. You can, at this Arduino site, you can download the software that lets you program it. It's free. It works on Windows, it works on Linux. I haven't tried it on the Mac, but it looks like it does. Also, if you're interested in using these things to do some magic, as we call it, okay, there are, well, actually I want to go back to that list. There are many, many Arduino boards that will work with the software, and they're all relatively cheap. You see all these Arduino BT, I don't know what that is. Leonardo's a new one that's even less expensive than the Uno, but only about 10 bucks or something less. LilyPad's fun. LilyPad is a round board designed for putting in clothes. So an example where that was used, I've seen an example, was in my human-computer interaction textbook last year. They built a jacket for bicycle riders, and it has arrows on the back. And they use an Arduino LilyPad in the jacket, and when the bike rider turned his head to the left arrow would blink. When they turned his head to the right arrow would blink. So there's an example of something else that's fun. All of these are minis, these are smaller versions, nano, little tiny ones that you can put in things, all programmed the same way. Oh, plus, there's these things called shields, which will let you do stuff just by plugging it in. You can, if you want to hook to the Ethernet, or basically the campus network, you buy an Ethernet shield, plug it in. Boom, it's doing it. Wireless shield will do wireless, Wi-Fi, stuff like that. Oh, I'm about to click on that, and that's not going to help me, is it? What was I going to say? Oh, yeah. Where's my, oh, no. Wait, am I doing this right? No, oh, there it is. Oh, that's the thing. Okay. A couple of pictures, there's the sites. Also, oh, where can you buy this stuff? That's a good point. SparkFun is a very popular one. There's other places you search. You can buy them on Amazon. You can probably buy them on eBay real cheap. But be careful. You don't want the undated ones. And, okay, what I want to do is bring up, we do it, excellent. With this. Okay, I want to show you some code. And I don't get scared. Oh. I want to go down here. It's not going to bite. It's very, very, very simple. Where's the zoom on this? And this is the code for this guy right here. Okay, and right now, he doesn't have any sensors, so he's not very autonomous, but he runs around, okay? And what I thought we'd try to do is, anyone familiar with barrel racing, right? we're going to do robot barrel racing. Only one barrel, not two. Traditional is two, right? Yeah. Oh, it's three. Oh, it's like, oh, okay. Well, one's good enough for a robot. Obviously, he's not doing very well right now, right? Okay. So, what do we need to do? Now, take a look at this code. And this is my little demo to prove to you that you can do this. What we've got built into the language is a thing called servo. Now, servo is another magic word. Let's see, let's unplug them while I'm doing this. And the things that are the motors on here are the servos. These are continuous rotation servos. And you can get other servos that you can set to different angles. You can play with that. We'll play with that maybe another time. So I create two servos. It's a library. It's pre-built. All I have to do is say, basically, I want to use servos. Here they are, right? Servo 1 and servo 2, okay? I'll come back to those in a second. On here, I attach the servo to a particular wire, okay? And the wires on here are just the places you plug in here, right? There's these places, well, if I pull one out, I might break it, but okay, I'll risk it. So this goes out, and I plug it back into here. It was 8 and 10, good, okay. There are numbers on here, so I can, but there are numbers, but if I get weak, I may have to have somebody else read them for me because my eyes aren't that good anymore. I get kind of lost. So we hook them to 8 and 10. We make sure, we don't worry about pin 13, then that's for something else. We set, or 10 and 8, we set them for output. And then we're going to tell them to stop, okay? And we're going to write something to it to stop, okay? Now the stop is just these up here. I made a bunch of things we call those variables, and if you're done in programming, and we just said, okay, stop means 90, right? S2 stop means 90, S1 stop means 90, okay? Don't worry about the numbers. They're all set to go. Forward means, note, I'll point out one thing. S1 forward is 95 and S2 forward is 85. Why do you think that is?
Does it allow turning motion?
Yeah. What's that? They're mounted reversed. One motor's this way, the other motor's this way. So forward on one is backward on the other, right? So, quick shot on that. So, obviously, let's see, I need an assistant to plug in on command. This is Chris Quintana, one of our prominent Robotics Society members. This is Matt Sadler, another prominent. And I mentioned Bradley Sisco, and we have a whole list. So obviously, just go ahead and plug them in. Start them at the white line, plug them in, and see what happens. So we want him to get up to the barrel, right? And oh, maybe he's doing all right. No, okay. No, he's sick, okay. So we want him to get all the way up to the barrel maybe, or close to up to the barrel. So you can see what the control here is S1, right? I just had him stopping to start, just stay stopped for a second. And then we're going to go forward for 2,500. That's in milliseconds. So how many seconds is 2,500 milliseconds?
2.5.
2.5, good. Got some scientists in the room, I guess, right? Okay. But it's obviously not enough, right? So we want to get further up to the barrel, so what do I want to do? Boost it up a little. So here, bring the bot over here. Yeah, there we go. Oh, you're going to be my stand and everything. What do you think? 3, 4, 4.5 seconds? 4.5? Okay. So 4.5 seconds. We just plugged this in. Let me see. I got to check one thing. Make sure it's still set right. Okay, good. And all we do here, oh, you can't see it, can you? All we do here is there's a button that says upload this program to the robot. And push the button, and it pauses for a second in anticipation. And so now that program is on this robot, on the Arduino, and controlling these guys. So let's see if that works. How are we doing time-wise? He's turning a little bit to the right. Okay, was that 4.5 seconds? That wasn't any 4.5 seconds. Okay, there he's starting off again. 1001, 1002, 1003, 1004. That was about 4. Yeah. That wasn't too bad. Okay, now he's not going straight, but maybe we can use that. Serendipity is a valuable tool. Okay, so we'll boost this up to 6,000, sorry. And yeah, ready? Okay, let's see if he, now point him right at the barrel this time. Now that right turn's not so bad, but maybe he needs to turn more to the right, right? So, okay, so where's that right turn happening? This is his stop. This is his right turn, where we stopped S2, right? S2, wait, or left turn, sorry. Was it a left turn? No, it was a right turn. Yeah, so we stopped S2, and there's where we stopped S2 and left S1 going. But he didn't turn far enough right, so a little longer right turn, right? So let's go with the 4.5. You can see how scientifically calculated this is, right? Oh. See, you already know. It's excellent. What's that? Oh, yes, I should put. You're right. That's right. That's right. That comes to this afternoon.
This is a good example of an iterative process.
Yes. Iterative. The word iterative. Some of you know my wife, Julie. When I use that word in normal conversation, she says, "You're just such a geek." And I do all the time. I am such a geek. Now he keeps turning more and more to the right on the first time. He's getting weak. Oh, that's not too bad. Oh, a little too much turning. Okay. Oh, maybe we just leave it there. That wasn't too bad. Maybe a little less turning. Let's what do you think? A whole second or a half a second?
At different rates?
Yeah, it looks like he's gotten a little bit, duct tape and poster board. He's gotten a little weak. He's not turning quite right. Is that what you said? I'm sorry.
Yeah.
I thought the wheels were rotating at different rates.
Yes, they are.
That's what's causing it.
Yeah, and that may be a drift also in these guys. Well, I could tweak that. He was on the straightforward, he was turning to the left, right?
Yeah.
So if we boosted,
He was going to the left.
he was veering to the left.
Yeah.
Right.
Okay, correct, yeah, right, yeah, I understand. Yeah, I have that problem too. Okay, so that means our S1's the guy on the left, is not going fast enough forward. So let's give him a little boost. Let's see what happens. Let's give him an 87. Oh, that's S2, sorry. Thank you. What would I do without you guys? Oh. Okay, there we go. So yeah, 97. I don't know how much, 95 maybe it's max, I'm not sure. And it won't hurt it if it is, it just won't go any faster. but I don't want to take this too much. You guys don't want to spend all afternoon doing this, right? We'll give it a couple more shots and see this. Oh, that's better. Well, obviously he's going straight too long. Okay. Who told me 65? And he's going to want to actually turn left, right? Well, we can turn right. We can turn right around, but that'll. He can go right and go that way. That'll work. We'll maybe give this a couple more minutes and call it good. Cross your fingers. Wait.
Set him back a little farther. Oh.
That's right. You know, like I said, out of the box problem solving. Literally out of the box. He wants pizza. Okay, well that's enough. I think you can see it's work, but it's not that bad. You know, we only spent what 15 minutes or so on that, 20 minutes maybe. So, you know, you can work it out, and we're sort of winging it. If you really think about, you can characterize the robot a little bit. You can be a little more precise. You can be a little bit more, oh, I measured him, he goes this fast, this many feet, this is how far it is, I can figure out the time delay, go backward. On top of that, what's even more interesting, of course, this is just a robot. I guess it's autonomous, but it's autonomous and brainless, right? What we'll add to this, what's added to these guys, have you got a sensor on yours yet, Cameron? No, not yet. What's added to like this guy are the sensors, right? So these guys, these are ultrasonic sensors, right? And they do essentially echolocation, echo distancing. So when it comes within a certain distance of something, it measures, sends back, it's actually another time delay issue, right? So it sends back a time delay, and you can figure out based on the speed of sound what that time delay is. If you really want to get particular, you can figure out what the air pressure is at this altitude and what the temperature that day is and plug those in and get a better estimate. So you can get pretty accurate estimates. This guy is set up, notice he has 3. So each ultrasonic sensor is 2 of these guys vertically. And the reason he has 3 is this is so he can see obstacles to his left, obstacles to his right, and obstacles in front of him. So if he's coming along, say the barrel, he'd come along this way. He'd say, oh, there's a barrel up there about a meter ahead of me onto the left. I'll veer a little bit to the right and get around. And he does when he's working, which he isn't right now. But what we'll be doing with the Robot Society today, and as we start up, the vision for the structure of this is this. We have old guard Robot Society, people from, really, old guard is a year, right? And we have a few of those. We have Cameron's here, anybody, and these guys are in there. Mike's been coming, Mike Anderson's been coming. And even though he wasn't doing it as much last year, we've decided he's old, so he has to be in the old guard. So, those guys have been working actually through the summer and actually started up this semester right off the bat. What's happening tonight is the newbie group. So I wanted to make sure that, and I wanted to do it that way, because if you're going, oh gosh, I don't want to get in this. First of all, you may have aversion to geeks and nerds, in which case you want to do that. You may be intimidated, right? So, because these guys know what they think they know, well, they say they know what they're doing, but you can come, and it'll all be new folks, and we'll have some of the old folks there to help you, right? And we'll show you how to do this. We've got Arduino boards out, we've got servos, we've got poster board, we've got duct tape, and what we're going to do is take the new group, through a process of building a robot, or if you want to build something else, that's fine too. Build something quick and easy, a prototype. If you have an idea that you think would make a good idea for the robot, or an idea that's good for something else, we'll show you, we'll help you do that. And then toward the middle to end of the semester, we'll try to encourage groups to form teams, okay? Team or teams, depending on how many people show up, to build a robot, or if you want to build one for the challenge, and start working on that process. Meanwhile, the old guard are working on this. They've already been building prototypes. So we're going to get this guy working for the robot challenge in the spring, and we'll be building another robot that will be a whole different approach. Plus, we have these robots, which you may want to look. Oh, I forgot to mention that. This summer, we did the STEM Academy, and that's where the black robot came from, by the way. And this one was built by high school students. It does a little. Oh. Go that way. Okay. And that, you can see that's not the most amazing. That was done. First of all, the robot was probably built in 2 or 3 days. This is Bob. And Bob is a demonstration of how to make a little more, oh, he fell over again. A little more active robot. Bob has a sensor, but he isn't using it right now. Actually, when his sensor's working, his eyes turn red when he sees something. So he does get angry. Yeah, yeah. And Bob is basically the same as this robot, only with a much nicer case.
Oh, he lost his front wheel.
Oh, finally. Yeah, we popped them off. We'll just unplug this first. Yeah, there we go. There we go. So, and this is Cameron's robot for the challenge. He's been working on it for, year 2, maybe? This guy, now correct me if I'm wrong, he's going to balance. He's like so he has a gyroscope and an accelerometer on him that tells him which direction is up. So he's going to balance and then walk along vertically, right? He balances pretty well, right, already. He's yet to take his first steps, but that will happen, okay? And this is another one that was quick. So, how we doing? Martin McKee made these, so. All right. Die, robot, die. Okay, there we go. So, where was I going? I was talking about, let's see. Oh. Where did we leave off? All participants. Oh yeah, way down here. Okay, and that's where we were left off. Start at the beginning. Just a quick recap of the PowerPoint. Oh, zoom out. Yeah, hold on. You're right. Well, you don't want to really watch all that, do you?
Just saying for later.
Yeah. Yeah, there's that one. Okay. And there we go. Okay, great. That's where we were. So come join us this afternoon. If you can't make it this afternoon, you want to come another time, please do. Contact me if you want, if you're interested. This is the group that we had last year. I think we got everybody in there. Note, the other issue is it's not just Adams State students. What we've got in here in this group, well, it's also Adams State University staff, right? So we've got those. We've got me, Cameron. Chris Dahl is a middle school teacher. I don't know if any of you guys know him. John Cheslock is a high school student. Rachel. is Benita's daughter, who's just starting middle school, right? And John is Benita's husband, who we really love, because he's got great ideas, but he also has the skills to produce them, which some of us try, and his stuff is just so good. Anyway, there's my contact information. If you're interested, any questions? I still got a little time for questions.
George?
Yeah.
Obviously, there's probably some sort of weight and size restrictions when used in practical applications, but at the dunes, do you have those limitations, or does everything go?
How should I say that? At the dunes, it's a, what's 1.8 or? 1.5 kilogram. That's the hard limitation. The soft limitation is 2.5, I think it is. And then virtually all the robots you saw in the images that we had of the Challengers, none of those met the 1.5 at all. Well, yeah, no, Cameron's does, but it wasn't running yet. But there was one other walker. Oh, and I forgot to run that walker. There was one other walker like this guy at the dunes, he was a little more sophisticated, but not much. Different kind of robot. Who that guy probably makes the weight restriction and things like that. So it's nobody's really policing it. But it's a sort of soft target, like, hey, we should try to keep it. This year, however, our group is really aiming for that 1.5 limit, just to sort of, it's sort of like, it's personal cred. It's like, if we came in with a robot that performed decently well under the 1.5 limit, we'd be like heroes.
And what comprises most of the weight? Is it power and the batteries?
Yes, actually motors and batteries probably the biggest part. Although some of the robots you saw there were made out of, they make them out of steel or metal, different kinds of metal. That aluminum's fairly light, but even that's fairly heavy when you start building that sizes. You build anything that's, well, even this size. Many of the robots were slightly larger than this guy. If you build anything that has motors and batteries that's that size, you almost are going to, it's hard to stay at the limit. So you have to go, the description at the consortium meeting was, you need to build something that weighs about as much as a small cat. And probably about that size. So, so he's a little too big. And just say goodbye to him as he walks out the door.
Wants to go out.
He might have done the barrel race pretty well. Other questions?
What kind of sensors are you using right now? You mentioned about the equidistance, but do you have any plans for the future also for sensors? Like I'm looking at what kind of sophistication are you planning on?
We look, the baseline ones that are really available are like the ultrasonic ones, or like there. We also infrared sensors, which use something similar, a sort of low-grade connect approach, where they project a couple of lines and then with a low-resolution camera decide how far the lines are apart and then judge distance that way. So that's one that's available. That's been used at the dunes several times, and they're fairly cheap and they're useful. What's that? Oh, yes, and feelers. Yes, that's another common thing is feelers with switches, so you bump into things. And we debate that off and on. It's like, why is infrared or ultrasonic any better? If the thing is isn't really going to do anything till it gets to the obstacle anyway, why not just have it bump into it and then say there it is, right? So that's another approach. Cameras have been discussed, trying to do like and I know you know something about that.
It's interesting because, as you said, there's a lot of intelligence which can be added on that one.
Yes.
You're talking about the sophistication depending on like the obstacle, the speed prediction, and tracking and stuff like that.
Yes. Oh, well, and that's another aspect that comes into this is if we want to try to do that has not really been done except last year one robot did it, and this is the ultimate, not the ultimate, it's one of the goals that we would like to have for most of those robots, is it builds a map. So this robot had an infrared sensor array and would turn and would try to build up a map of the obstacles, and then plan its path beyond that. Yeah, which is.